Hey guys, in today's video, we're going to be talking about the law of conservation of energy, or just conservation of energy for short. And we see this law consistent through different scenarios we'll see in a lot of physics, like maybe roller coasters or bouncy balls or a ball falling off a plane. And in all of these scenarios, the law of conservation of energy is being used. So in today's video, I'll show you exactly what that means. I'll hope to give you some type of conceptual understanding over it. And we can break it down to some simple examples that will help you solve some problems on homework or exams. So let's begin. First off, what even is energy? Well, energy in physics is the ability to do work or cause change. There's a lot of different types of energy. Like we have two you may already know, the first of which being kinetic energy, and the second of which being potential energy. Kinetic energy is your energy of motion, and potential is your stored energy, and it's based off position, like height. And these two energies added together equals mechanical energy. So mechanical energy is the sum of these two. And for these two types of energies, we'll use two formulas. For kinetic, we'll use 1/2 mv squared. And for potential, we'll use mgh, with m being mass, v for velocity, g for gravity, and h for height. Let's start with a sort of visual situation for this. Let's say I attach a ball to the ceiling, and we're going to assume here that the ball isn't moving. Now, here's the key idea of the law of conservation of energy. It's that energy cannot be created nor destroyed, which is a phrase you probably have heard before. And energy can only be transferred or transformed. And that is the main principle behind the law of conservation of energy. So if I'm holding this ball at some height, it has potential energy, right? Because we know potential energy, as we said, equals mgh. So if it has some height, that means it has some potential energy. And we're assuming the ball is not moving, which means kinetic energy, which equals 1/2 mv squared. If velocity is 0, because the ball is not moving, kinetic energy would have to be 0 in this case. So, as we said, it has potential energy, no kinetic right now. Now, let's say I cut the rope hanging the ball, and the ball begins to fall. So, this is it falling down. As it falls, it loses potential energy, but gains kinetic. But the total mechanical energy is going to stay constant, because however much potential it lost is however much kinetic energy it gained. And as we know, mechanical energy is the sum of these two, so it'll stay constant. And that's assuming there's no friction or air resistance. So the equation for the law of conservation of energy is going to be this then. Your initial kinetic energy plus your initial potential energy is going to equal your final kinetic energy plus your final potential energy. And that's our conservation equation. So let's use it. Let's go ahead with an example problem. Let's think. So let's use our ball again. So I go ahead and I drop our ball from rest from a height of 10 meters. So height is 10 meters. And let's say that this ball is 2 kilograms. What is its speed before hitting the ground? We're looking for velocity here. So let's start out with the conservation formula that we just talked about. So we have kinetic energy initial plus potential energy initial equals kinetic energy, that's a weird looking K, final. I'm going to fix that. Kinetic energy final plus potential energy final. So, as I said, it starts from rest. So our initial kinetic energy would have to be what? 0. And we said that it starts from some height, as I said, 10 meters over here. So there is some potential energy initially. So mgh. And I'm going to put a little I by the h because it starts at some initial height, right? We're trying to find the velocity right before hitting the ground. So 1/2 mv squared. And I'm going to put a f right next to velocity just to show its final velocity. And we're assuming that over here with our initial kinetic energy, velocity there would have been our initial velocity, which was 0. And that's going to be plus 0. I know I said that this is right just before hitting the ground, but if we're talking about just before hitting the ground, that height is so small, it's basically negligible. So that's why we're saying it's 0. So we can erase these 2 zeros, which will give us that our initial potential energy is going to equal our final kinetic energy. So now from here, we let's isolate for V. That'll be easier for us. So first, let's just cancel out m from both sides. So we'll take out m, and that'll give us 1/2 V final squared equals g times height initial. Let's multiply by 2 on both sides to cancel out this 1/2. And let's square root everything. And that will end up giving us, just using some algebra here, that V final is equal to the square root of 2 times g times h. And if we just plug in our numbers here, we have V final equals the square root of 2 times, we're going to use 9.8 for gravity, 9.8 times our height, which is 10. And if I put this in my calculator I have here, we'll get a final velocity of about 14 meters per second, we'll say. Yeah, so a 2 kilogram ball, actually, well, as we saw, mass didn't matter here because it canceled out on both sides. So it could have been really a ball of any mass here. If we started at a height of 10 meters, it would have been at a velocity of 14 meters per second just before hitting the ground. Right. So let's talk about a different example now. I mentioned roller coasters in the beginning, so let's talk about a roller coaster. So let's say I have like a little roller coaster track here. And at the top of the hill, let's say I have my roller coaster. So That's my roller coaster here. There's the little carts. At the top of a hill, it has its max possible potential energy. This is because it has no velocity. We're saying at the top of a hill, it's basically not moving. It's also at its max height at the top of a hill, so that's why it has its max potential energy. And as it comes down, since its velocity is increasing, we'll know that potential energy is being transformed into kinetic energy. But what's cool about this is if we assume no friction, the total energy won't change throughout the ride. So we can show this kind of using energy bar charts. So at the top of the hill, we'll have 100% potential energy, and I'm going to denote zero kinetic energy just with a line. We'll have zero kinetic energy. At this middle portion here, I know I didn't draw a very good hill, but at this middle portion here, we'll have about 50 potential energy, 50% potential, 50% kinetic. And at the bottom of the hill, this will be zero potential energy and 100% kinetic energy here. So that's a way to look at it conceptually in the situation of a roller coaster. Now I'm going to give you guys a little example problem that you guys can do real quick. So let's say we have let's make the roller coaster track again, and let's make it a little better this time. Let's say a 500 kilogram roller coaster. So mass is 500 kg. It's going to start at a height of 20 meters. So let's say it starts like here. Sure, this will be 20 meters. It starts at a height of 20 meters. What is its speed at a height of 5 meters? And I'll give you guys a quick second to pause the video and try solving that one for yourself. All right. So at the top, we only have initial potential energy, right? So, and we have no initial kinetic. So I'm just going to show that by just putting mgh initial. And as it's going down to a height of 5 meters, we're still going to have some potential energy, just less, because it still has some height, 5 meters, but just less. But where did that potential go that it lost from going from 20 meters to 5 meters? Well, it got transformed into kinetic energy. So we'll know that we have some final kinetic energy and some final potential energy, right? So now we just solve and plug in. So cancel out all of our m's here, m's. So now we'll have g height initial equals 1/2 v final squared plus g height final. We can just plug in all these numbers, and I have the answer already prepped and ready for me. We should get that velocity final is about 17.1 meters per second. All right. So now let me clear up some common misunderstandings with this. One of them is that people forget that energy is a scalar, not a vector. So if you're taking AP Physics 1 or some other physics course right now, you probably learned that like way at the start of the year, that energy, or just the difference between scalars and vectors in general. Energy is a scalar, so it doesn't have direction. So energy scalar. Also, don't forget that only mechanical energy is conserved, not thermal or sound energy unless stated. In this video, we were only talking about mechanical energy, so that should give you a hint. And in every problem, assume that friction is 0. Unless it's stated. So always check. Just do a quick glance through the problem. Check if there's some coefficient of friction or some form of friction somewhere. Right. And in real life, energy isn't perfectly conserved, right? Perfectly conserved mechanically, because some is lost to heat, friction, or sound. But the total energy of the system is always conserved. And we'll see this, like, if you drop a bouncy ball and put it in slow motion and set up a camera, you'll see that when you drop it and as it rebounds, its rebound height will never make it to what the initial height is. And that just shows how an energy isn't perfectly conserved mechanically. So I guess that's conservation of energy in a nutshell. Energy just changes forms, and its mechanical energy is conserved. So if this helped, drop a like and comment below with a topic you want to explain next. And thank you guys. Have a good one.